Hey everyone, today we're going to continue exploring techniques of integration, and what we're going to talk about is the procedures involved in integrating products of trig functions. So that's the topic here, products of trig functions. And to do so, we're going to need to think back or remember back to certain trig identities that you learned probably when you're taking pre-calculus. And so these are identities that you'll need to have memorized. You need to know these for this class and for future classes when you're integrating products of trig functions. And so let's run through the ones that we're going to need. The first one, this is your standard cosine squared x plus sine squared x equals 1. I'm sure all of you remember this one. Now, there's a couple here that are sort of related. So cosine squared x is equal to 1/2 times 1 plus cosine 2x. And also with number 3, so this is sine squared x is equal to 1/2 times 1 minus cosine of 2x. So we'll need both of these. The next one is a direct result of identity number 1. And so before I write it down, let me just remind you how this one comes about. So identity number 1 gives a connection between cosine squared and sine squared. When you add them together, you get 1. Now, by dividing everything in this equation by cosine squared, notice what we get. We get 1 plus, here we have a tangent squared, and on the right-hand side of this equation, we have secant squared. So, by dividing our original identity number 1 by cosine squared, what we get is a connection between tangent squared and secant squared. So, 1 plus tangent squared x equals secant squared x. So this is another one that you should have memorized. You're going to need all of these. But if you ever forget how this equation goes, you can always rederive it by taking this equation and dividing everything by cosine. And you should notice also, I divided by cosine squared here. If I divided by sine squared, that would give us a relationship. I'm not going to write this one down, but it gives a relationship between cotangent and cosecant squared. Okay, identity number 5, that's going to be sine 2x is equal to 2 cosine x times sine x. And then the last one we need, so number 6, cosine 2x is equal to cosine squared x minus sine squared x. Right? So these 6 identities we're going to need for this section, for the next section, and anytime products of trig functions and their integrals come up throughout calculus, you're going to need these identities. So let's see how or why we need these identities when it comes to integration. And so we're just going to work through examples now. So first example, let's integrate, so let's do integral of cosine squared x dx. Now, we don't have a formula for the integral of cosine squared, so what do? We say, oh, according to identity number 2, we can replace our integrand with 1/2 1 plus cosine 2x. And then when we simplify things, so I'm going to pull the 1/2 out and write this as a 1 plus cosine 2x. And now what we have is an easy integrand, right? So this comes out to be a 1/2 times x plus 1/2 sine 2x plus c. If you like, you can simplify this a little bit, but there's the answer. Right? So the point is, if you see a cosine squared, apply identity number 2. And I want to sort of annotate this step right here. I applied identity number 2. If you see an integral involving sine squared, apply identity number 3 and then use this same process right here. Once you've applied that identity, it gives you a relatively easy integral to compute. So there's our first example. Next example, let's look at sine cubed x. Now, I'm just going to work this one out and show it how it goes. So sine cubed, that means sine x times sine squared x dx. I peeled one factor of sine off of this. Now, I'm going to apply an identity. If you look at identity number 1 and solve for sine squared is equal to 1 minus cosine squared x dx. All right, so what I did from here to here, I applied trig identity number 1. Just solve in that identity, just solve for sine x. And now, why I did this, or how this, what this does, is it allows us to use substitution, where I'm now going to let u equal cosine x, du equals minus sine x dx. And so now when we substitute, what this becomes is integral. Well, it's actually negative from that minus sign right there. So negative, the sine x's cancel out, and we'll have a 1 minus u squared du. I don't really like that minus sign, so I'm going to distribute it through, and I'll get a u squared minus 1 du. And now we've got an easy integral by applying this identity, making the appropriate substitution. We converted an integral of products of trig functions into the integral of a polynomial. That's something we know how to do easily. This gives us a u cubed over 3 minus u plus c. And when we substitute back, what we'll get is cosine cubed x over 3 minus cosine x plus c. So remember this, and we're going to do some similar examples like this. The idea was by peeling off a factor of sine, we were able to apply an identity. And we'll talk about the theory a little bit more. Let me look at another example. And it's sort of similar. So next example. Let's do cosine cubed x times sine to the 4th x dx. Now what I'm going to do is I'm going to peel off one factor of cosine x. So now we'll have cosine x times cosine squared x times sine to the 4th x dx. Now I can apply identity number 1 to that cosine squared right there. So it's going to go like this: cosine x times 1 minus sine squared x times sine to the 4th x dx. So what I did right here, I applied identity number 1 to the part I have circled right there. If you solve for cosine squared in identity number 1, you get 1 minus sine squared. Now, why is this useful? Why did I do this? Because now we're in position to do substitution where I let u equal sine x. In which case du equals cosine x. And when we substitute back, what we'll have is a 1 minus u squared times u to the 4th du. So by peeling off a factor of cosine and then applying identity number 1, we're set up to do substitution and convert the original polynomial into, or original integral into that of a polynomial. So let's finish this off. What we have is u to the 4th minus u to the 6th du. And now we can compute the integral. That's a u to the 5th over 5 minus u to the 7th over 7 plus c. Substitute back. That's going to be a sine to the 5th x over 5 minus sine to the 7th x over 7 plus c. So before I go on to the next example, I want to talk about why this worked. We did two examples. The first one was a sine cubed. The next one was cosine cubed times sine to the 4th. And the question I want to ask you, unfortunately I'm not here to actually answer the question, but the question I want to ask is, why did this trick work? Why did this peeling off a factor of sine or cosine actually work? And the answer is, or what was special about each of these integrals, it was the odd power. Right? In sine, when I integrated sine cubed, remember what happened? We got a sine x times sine squared x dx. Because it was odd, when I peel off one factor of sine, I get an even power of sine. That's where I could apply identity number 1. Same thing here. Why did this work? Because I had an odd power of cosine. By peeling off one factor of cosine, I got an even power of cosine, for which I could apply identity number 1. That sets us up to do substitution, because when you let u equal the sine, the derivative canceled off that extra factor, that peeled off factor of cosine. So this trick works whenever you have either an odd power of cosine or an odd power of sine, or odd powers of both. Right? That trick will work. So odd power of either sine or cosine, that's great. Even power is a little more tedious, I guess I should say. So let's look at this example now. Let's do cosine, what was it, cosine squared x times sine to the 4th x dx. And when both powers are even, now it's kind of a pain. What you have to do, and I'm not even going to carry this all the way out, but let's just see how it goes. When you have an an even power of both sine and cosine, what you're going to do is repeatedly apply identities number 2 and 3. And so what this becomes is, so let's see, we'll have a 1/2 times 1 plus cosine 2x. That's applying identity 2 right here. And then we will also have 1/2 times 1 minus cosine 2x, all of that squared, dx. So what just happened, for the cosine squared, I applied identity number 2 directly. For the sine to the 4th, remember, sine to the 4th is sine squared x squared. And so I've applied identity number 3 to the sine squared portion, and then outside we have it squared. So just to indicate what we did, we used both identity 2 and 3 right there. All right, so now let's clean things up a little bit. This is a 1/2, 1 plus cosine 2x times 1/4, 1 minus cosine 2x squared dx. And I don't want to complete this. This one gets a little bit too messy eventually, or at least too messy for you to watch me do. But now what I'm going to do is I'm going to multiply this piece out right here, and what we get is a 1 minus 2 cosine 2x plus plus cosine squared 2x dx. Now I got to multiply this mess out. So you can see when you have both even powers, it kind of becomes a mess. But here's the point. Applying identities 2 and 3, take the squared and reduce it to a first power. Take the fourth power and reduce things to a second power, right? So the identities reduce the power, and by repeatedly applying these identities, we're actually going to get down to something that we can integrate. So let me take this a little bit further by multiplying this stuff out. And you'll see, I mean, there's nothing difficult, it's a lot of writing. So let's see, if I multiply this out, we're going to have a 1 minus 2 cosine 2x. Oh, 2 cosine 2x, not squared. Cosine 2x plus cosine squared 2x plus cosine 2x minus 2 cosine squared 2x. And then the last term is going to be a plus cosine cubed. Sorry, I got to write it down here. Plus cosine cubed 2x dx. Okay, then, so next step, so let's multiply things out. Or actually, I'm going to clean things up a little bit here. So this is going to be a 1. And here we're going to have so that's just going to be minus cosine 2x. And then we have minus cosine squared 2x plus cosine cubed 2x dx. So we're almost in a position where we can integrate. Now what I want to do is get it into that position. So notice we know how to integrate all but one of these pieces at this point, right? The one, obviously, cosine 2x, no problem. Cosine cubed 2x, we just learned if you have an odd power of cosine, there's a technique for integrating that. The only one is how do we handle this cosine squared? Well, we need to apply identity number 2 one more time. So it'll be a 1 minus cosine 2x minus 1/2 times 1 plus cosine 4x plus cosine cubed 2x dx. So let me write down one more piece here, or do one more step in the simplification process. This becomes a 1/8 integral. So this will be a 1/2 minus cosine 2x minus 1/2 cosine 4x plus cosine cubed 2x dx. So I agree it's a little bit tedious. Oh, and by the way, let me just mark right here at that step, I applied identity 2. Right? Converting this cosine squared to that piece right there. Now I've got an integral for which I can compute. I don't want to belabor this anymore, but the idea is if you have even powers of sines and cosines, apply identities 2 and 3 repeatedly until you get everything into reduced powers. Right? So we actually now know everything we need to know, so I want to write down a general procedure for integrating powers of sines and cosines. So if we have sine, say, mx times cosine nx dx. Now there's 3 possibilities, and that's going to be whether this power is even or odd, or both even. So let's see, if m is odd, so if we have an odd power of sine, peel off 1 power of sine x, peel off a sine x, apply identity number 3, and then what you'll have is you'll have one factor of sine, everything else will involve cosine, and so then you let u equal cosine x. If you do that, guaranteed that's going to convert the original integral into that of a polynomial. Second possibility, if n is odd, then, so now we've got an odd power of cosine, peel off cosine x. Oh, sorry, I made one mistake here. It's not apply number 3. Sorry, it's apply identity number 1. Sorry. Peel off cosine x, apply identity number 1 again, but now you're going to let u equal sine x. These steps right here will convert the integral into that of a polynomial. The last option, if they're both even, so if m and n are both even, apply number 2 and or number 3. So it is a bit tedious in that case. Crank it out. Eventually you'll get to pieces of the integrand for which you can compute. Okay, so let's move on to some new examples here. Let's look at integral of tangent to the 4th x, secant to the 4th x dx. And I remember when we had odd powers of either sine or cosine, the point was we peel off either a sine or cosine, whichever was odd. That enabled us to apply an identity to get everything in terms of the other trig function, and you just have this dangling sine or cosine. And that sine or cosine was the derivative of whatever was left in the integral. So let's think about that now as we work on this example. What I'm going to do is I'm going to peel off a secant squared. All right, so I can write it as tangent to the 4th x, secant squared x, secant squared x. Now, why is that? What am I going to let u equal? Well, if I let u equal tangent, the derivative of tangent is secant squared. That's why I'm peeling off a secant squared. Okay, so now I can apply identity number, this is going to be identity number 4 here. So we'll have a tangent to the 4th x times a 1 plus tangent squared x times secant squared x dx. So here what I did is I applied identity number 4. Now, why does this help? Because if I let u equal tangent now, right, so notice everything's in terms of tangent except for this part that I peeled off. If I let u equal tangent, its derivative will be secant squared. We'll get rid of that secant squared. We'll have a polynomial. So we let u equal tangent x du equals secant squared x dx. And now what we're left with, we get integral, so this will be a u to the 4th times a 1 plus u squared du. Multiply this out, we'll get a u to the 4th, plus u to the 6th du. That'll give us a u to the 5th over 5 plus u to the 7th over 7 plus c. And when we substitute back, final answer will be a tangent to the 5th x over 5 plus tangent to the 7th x over 7 plus c. Now, why did this one work? Okay, so let's think about what we needed. We wanted to get the entire integrand in terms of tangent except for the portion that we peeled off. And we needed then, if it was all going to be in terms of tangent, we're going to let u equal tangent so that du equals secant squared. Now, I needed to be able to get everything in terms of tangent, I needed to be able to apply identity number 4. So I needed to be able to peel off a secant squared and have a portion remaining for which I could apply identity number 4. The reason this worked, that power right there was even. When you have an even power of secant, this trick of peeling off a secant squared is going to work. Another combination, so let's do another example of combinations of secants and tangents. So let's do tangent cubed times secant to the 5th. All right, so we've sort of established this idea that we want to peel off something, and that something should be the derivative of whatever's going to remain after applying an identity. So in this case, what I'd like to do, you can see what I'm doing here, I'm going to peel off a factor of tangent and a factor of secant. So what we'll have now is a secant x tangent x dx. So what do you imagine in the end, what I'm going to let u equal? I'm going to let u equal secant x so that the derivative will be secant x times tangent x. Next step, I need to apply the identity. So we have, what do we have? Tangent, sorry. Identity number 4 tells me that this is equal to secant squared x minus 1, and then we have a secant to the 4th x, secant x, tangent x dx. So here, I applied the identity number 4 to that tangent squared. Okay, so now if we let u equal secant x, du equals secant x, tangent x dx. And this substitution has converted our original integral into that of a polynomial, which we can easily compute. So this will be a u squared minus 1 times u to the 4th du. That's equal to u to the 6th minus u to the 4th du. That's going to give me a u to the 7th over 7 minus u to the 5th over 5 plus c. And when we substitute back, what we'll get is a secant to the 7th x over 7 minus secant to the 5th x over 5 plus c. Why did this work? I needed to be able to peel off a secant x and a tangent x and then apply identity number 4 to the tangent portion, which means, since I peeled off a tangent over here, I needed an odd power of tangent. So this trick worked because I had an odd power of tangent. So this allows us to write down a general procedure now. So we've seen the possibilities that work out for products of secants and tangents. So let's write down our general procedure. Now this general procedure does not handle all the possibilities. The one for sines and cosines does, right? No matter what, it's either they're both even or one of them's odd. As soon as one of them's odd, we know what to do. So general procedure for integral secant to the mx tangent to the nx dx. So first possibility, if m is even, peel off a factor of secant squared x, apply identity number 4, and let u equal tangent x. And then the second possibility, if n is odd, peel off a secant x, tangent x, apply number 4, and then let u equal secant x. So in the situation where m is odd and n is even, this procedure does not work. And so there are situations that are not going to fall under our general procedure. In that case, you just have to try something. So one piece of advice, when in doubt, when it doesn't fall under one of our general procedures, a good idea, convert everything to sines and cosines. A lot of times things will collapse and give you an easy integral. That doesn't always work, but that's at least one of the things, or one approach that you might take. And I should just point out, so there's a similar procedure for integral of cosecant mx cotangent nx dx. We've talked, or you learned long ago, the integral of sine and cosine. We just learned how to integrate some products of secants and tangents, some products of sines and cosines. We also talked a couple of weeks ago, or a couple of lectures ago, let's say, about the integral of tangent. And I just want to remind you how that goes. So integral of tangent is one that you should have memorized. And the way you do this, to get the formula, you rewrite it as sine over cosine. Now it's set up to do substitution where you let u equal cosine x, du equals minus sine x dx. And so this becomes then integral of, well, it'll be negative, let me put the minus sign out front, minus integral 1 over u du. And then this becomes negative natural log, absolute value of u plus c. If you substitute back, what we get is negative natural log, absolute value of cosine x plus c. And so when we learned the formula for the integral of tangent last time, this is the way we left it. But remember now, there's a rule of logs that says that we can bring this minus sign up as an exponent. And so we can rewrite this as natural log of absolute value cosine of x raised to the minus 1. And the reciprocal of cosine is secant. And so typically, let me write this as a formula now. Typically, the way the formula for the integral of tangent is written, to get rid of these minus signs, you can rewrite this as natural log absolute value secant x plus c. So that's the way you want to memorize that formula. You should understand how this formula comes about, but that's the formula. A similar process you can go through to find the integral of cotangent x dx, and this one turns out to be natural log absolute value of sine x plus c. So you want to commit both of those to memory. And so that means now that we have the formulas for 4 of the 6 trig functions, and now let's get the other 2 out of the way. So let's look at the secant now. All right, that's another one that at this moment we do not know a formula for the integral of secant. And this one requires a trick that you're definitely not expected to understand why someone smart came up with this trick. You're also not expected to memorize the trick. You should memorize the formula once we get to it. But here's the idea. What we're going to do is we're going to multiply by 1 in a clever way. And the clever way, secant x plus tangent x divided by secant x plus tangent x dx. Right? So there's no real reason at this moment to think, oh, that's the obvious thing to do. But now let's multiply things out and see why this works. What we get is a secant squared x plus secant x tangent x in the numerator, and the denominator is secant x plus tangent x. So here's the point. Think about now, what is the derivative of the denominator? Well, if you take the derivative of secant is secant x plus tangent x. Derivative of tangent is secant squared. So this is now set up to do substitution where we let u equal the denominator. In which case, the derivative is equal to the numerator. which means that we've converted our integral into integral of 1 over u du. That's equal to natural log absolute value of u plus c. And when we substitute back, what we'll get is natural log absolute value secant x plus tangent x plus c. So let's write that down, and this is another one that you want to memorize. The integral of secant x is equal to natural log absolute value secant x plus tangent x plus c. A similar trick will allow you to integrate cosecant x. And it turns out this one is equal to natural log absolute value cosecant x minus cotangent x plus c. That's another one. Just memorize that one. Now we have formulas for all 6 of our trig functions. So I want to do a few more just sort of miscellaneous trig functions or integrals of trig functions. So a few more examples here. Remember, we have a formula if we have an even power of secant and an odd power of tangent. In this case now, I've got an even power of tangent. So what do we do here? Here's an idea. All right, and sometimes you just have to try something. Switching to sines and cosines can sometimes be useful, but in this case, I want to make use of identity number 4. So I'm going to rewrite this as tangent squared x times tangent squared x, right? So just split that up. And then I'm going to apply identity number 4. This is a secant squared x minus 1 times tangent squared x dx. And now, if I multiply this out, what we'll get is a secant squared x tangent squared x minus tangent squared x. So, oh, and let me just note right here is where I applied identity number 4. Okay, now if we look at this integral, I can integrate this piece right here by letting u equal tangent x, the du will equal secant x. But I still have this tangent squared x. Notice what I can do. I can again apply identity number 4. And now I've got pieces, every one of which I can integrate. So I'm not going to go all the way through this, but here's the idea. By repeatedly applying identity number 4, we were able to get it in position where we could actually integrate. And that's typical when you have just an even power of tangent and nothing else in there. Apply this trick right here. I guess I probably shouldn't even call it a trick, right? But apply the identity. Next example. Let's look at integral of, where'd it go? Cosine squared x times sine 2x dx. Notice we haven't used identities 5 or 6 yet. Here's a place where using one of those will help. So there's actually 2 different ways to do this. One way is to apply identity number, which one was it? I think I called this one number 6. No, sorry, identity number 5. All right, sine 2x is equal to 2 times sine x cosine x. So here, apply identity number 5. That would give us, let me put the 2 out front, 2 times cosine cubed x sine x dx. This is set up for doing substitution. Just let u equal cosine. Or maybe you saw, oh, I see a cosine squared there. You could also apply identity number, this would be identity number 2. You could write this as 1/2, 1 plus cosine 2x times sine 2x dx. This is a little less direct. It takes a little bit more work. But then if you multiply this stuff out, you'll have a cosine times a sine. You could set up to do substitution there. All right, so either one of those works. Here, I guess I applied, what did I apply? Identity number 2. Right there. So sometimes there's more than one correct, in fact, often there's more than one correct way to do it. So let's end here, and I want to I'll just write this down. So when in doubt, apply, switch to sines and cosines. Right? I mean, that's not always the correct way to do it. But if I get stuck, I mean, sometimes you're handed an integral, it doesn't fit with any of the general procedures. I try various identities, seeing what I can do, splitting things up. Sometimes, as I guess I could call it a last resort, I switch to sines and cosines, and often things will fall apart. So integrating trig functions takes some work. Right? There are certain general procedures that work in certain specialized cases, but not all of the situations fall under those categories. Right? So sometimes you just have to try something. Okay, so we will see you next time.